All right, welcome back, everyone. It's time to break down another really common system design problem. This time we're going to take on web crawler. I think web crawler needs no introduction. It's a super popular problem. I'm sure you've all heard it a number of times, but now you're going to get my take on it. So apologies, this video is a little bit late, a week later than I usually like to do. I was traveling, bear with me. We got the hat on. Was feeling a little too lazy to shower this morning. So hopefully it won't have any negative impact on our system design skills. But for those who haven't seen this video, you're seeing it for the first time, quick introduction. My name's Evan. I'm a former staff engineer and interviewer at Meta. And I've asked all of these questions dozens, tens, in some cases hundreds of times. So in this kind of series of videos, we walk through a system design problem together. I point out exactly what interviewers are looking for at the different levels based on my experience. Now, I said former staff engineer at Meta. I spend my days nowadays as the co-founder of Hello Interview. And at Hello Interview, we help candidates prepare for upcoming interviews. And this is largely via in-person mocks with FANG, senior plus engineers and managers like myself. So if that's something that you're interested in, head over to hellointerview.com and take a look. Now, before I jump in, videos might not be your thing. That's totally fine. I also wrote up a detailed written kind of guide to this problem. So if you head over to Hello Interview, you can check out Design a Web Crawler. You can go through it, see all my tips there, break down good, bad, and great solutions. You'll see that we also have about 11 other common problem breakdowns here on the side. Take a look at those, as well as how we recommend that you approach system design interviews in the first place. Lastly, you click on that suggest a question, and you can let us know what we should do next. So feel free to either propose a question or just vote as you see here. All right, without further ado, let's jump into it and design a web crawler. All right, so before we jump into actually solving the problem, let's just take a really quick moment to talk about the roadmap that we're going to follow throughout this interview. And this is the roadmap that I suggest that you follow in any of your system design interviews. So the very first thing that we're going to do is we're going to define the requirements of the system. This is the functional requirements, or the features of the system, as well as the non-functional requirements, the qualities and constraints of the system. We're then going to just document the core entities. This is just a list of basically like the tables that you would have. I don't go into the full schema yet because oftentimes this early in the interview, I don't know it. So I kind of communicate with the interviewer that I'm going to come back and maybe I'll fill out this full schema as I need to. But that's where we go next. Third is that we talk about either the API in the case of a user-facing application, or in the case of something like a web crawler, the interface. So just the inputs and outputs of the system. Fourth, and this one's optional depending on the system, but for something like web crawler, we'll do it because it's going to be really useful. And that's to enumerate how data is going to flow through our system. And this is important because we're actually going to use that enumeration of the different steps in a web crawler in order to inform our high-level design. And so step 5, high-level design, is where we head to the whiteboard and things start to get fun. We draw out a simple diagram that is able to fulfill, and this is crucial, our functional requirements of our system. So at this point, the design should be really straightforward. It should be really simple, and it just meets those functional requirements. Now, step 6, deep dives, is where you really earn your value, particularly as a senior candidate, staff plus candidate. This is where you go back to those non-functional requirements and you evolve your high-level design one by one through each non-functional requirement such that your ultimate design eventually satisfies the functional and non-functional requirements of your system. So that's the process that we're going to follow. You're going to get to watch me walk through exactly that now. Before we get into those functional requirements, just quickly, what is a web crawler? And so a web crawler is a program that automatically traverses the internet, traverses the web, and it does this by downloading pages and then following links from one page to another and repeating that process recursively. And so it's used to index the web for search engines like Google, for collecting data for research maybe, monitoring websites for changes, collecting data to train machine learning models, etc. And so if you get told to design a web crawler in an interview, the first question you might want to ask is, well, what's the purpose of the web crawler? What am I going to be using it for? Because that's going to have some consequences to your design. So I narrow in our scope here. This is the problem definition that you can assume the interviewer gave you. This is actually the version that I ask. And it's to design a web crawler that extracts text data from the web and stores it with the goal being to use that text data to train an LLM, a large language model, like OpenAI's ChatGPT. And so your crawler, this is an additional constraint that I provide, your crawler can only run for 5 days. We need this data quick. Like OpenAI is killing it. They have ChatGPT. We're maybe over at Google, or we're over at Microsoft or Apple or wherever, Facebook. And so we need to get this data ASAP so we can start training this model. So that's kind of an additional constraint there. Notably, of course, this design isn't going to go into training the model, even the tokenization, any of that. Our job ends when we store that text data, and then that's where the machine learning team can pick it up from there. So that's the problem definitions. Now let's jump right into the functional requirements. So those functional requirements are relatively straightforward for a problem like this. I'm actually just going to paste them in so you don't all have to watch me struggle to type. But we just need to be able to crawl the full web, starting from a set of seed URLs. We'll define that here in a second. And then we need to extract text data from those websites and store them somewhere, probably in a database. Now, before I get into the non-functional requirements, I would pause and ask my interviewer a little bit about the scale of the system. So I might ask them, how many websites are there? And maybe they tell me, or maybe they ask me to estimate. But in either case, I'm going to say 10 billion web pages. And then I'm going to estimate that a web page on average is maybe 2 megabytes. So per page on average. Maybe I asked them for this. Maybe I estimated it myself. And then we already know that we have 5 days to scrape. So there's some scale, some constraints that we need to know. I might also ask them, who are we? Are we a big organization that kind of has infinite resources from a money perspective? Or do we need to be really cost conscientious, etc.? In this case, I'm going to say, unlimited resources. Within reason. So within reason. That's what we'll design for. And so now we move on to those non-functional requirements. And non-functional requirements, they're the how of your system. They're the constraints that your system must operate under. So let's kind of think of some that make sense for us here. In the case of web crawler, some non-functional requirements that stick out as interesting are things like we need to be fault tolerant. And this is because we need to be able to handle failures gracefully so that we can resume crawling without losing a ton of progress. It would suck if we got maybe halfway through crawling and then we lost everything that we had been working towards. That would certainly be a bummer. Another one that's really common for web crawlers is something called politeness. And so politeness is adhering to robots.txt in order to not overload website servers inappropriately. So websites can have a robots.txt on their servers, which defines how often they can be crawled. And so we don't want to be hitting any given website over and over and over again, effectively DDoSing it such that site goes down. That would be inappropriate, bad practice, and something that we want to avoid doing. So we'll see some examples of robots.txt and how to adhere to it later in the interview. Another thing is that, of course, we need to be able to scale to those 10 billion pages. So we need to be able to handle scalability in order to get up to 10 billion pages. That's quite a bit. And then another one here is that we need to be efficient. And efficiency here means the efficiency to crawl the web page in under 5 days. So crawl in under 5 days. And so those questions were important because non-functional requirements, to the extent that it's reasonable, should be quantified. And so by understanding the scale of our system, we were able to better quantify here efficiently. Right? So there's the functional, scale, and non-functional requirements of our system. Now I'm going to just take a quick moment to note that in many things that you read online, etc., they'll encourage you to do back of the envelope estimations at this point. I'm not going to do that. And if you've seen many of my YouTube videos, you'll know my opinion on this. But estimations are important. They're actually very important. And we'll do some later on. But what I find in conducting so many of these interviews is that candidates just take a moment to do this basic math about scale, about throughput, daily active users when that's relevant, etc. And then at the end of that math, they say, wow, that's a lot. And then they keep going. And what I learned as an interviewer is absolutely nothing other than the fact that you can do basic math. And what you learned as a candidate is equally nothing. You learned that you're going to create a distributed system. Yeah, of course. We kind of knew that when we asked some questions about the scale of a system. So instead, it's my suggestion to you that you communicate with your interviewer at this point. That's very crucial. Communicate with your interviewer that I'm actually not going to do math at this point because I want the calculations that I do to directly influence or inform my design. and I don't have math at this point that will do that. So while I'm designing, maybe in my high-level design or deep dives, if I have a critical junction for which math will inform my direction, I'm going to do math at that point. And in my opinion, this is much more sophisticated. It's more realistic. It's more indicative of what you would do on the real job. So take it or leave it. That's my suggestion for you there. All in all, we have the problem set up, and now it's time for us to jump into that next step, which is the core entities, the interface, and the data flow. Following along with our roadmap, we move on to the core entities. The core entities are meant to help you understand the data central to your design, and they're going to give you a foundation to build upon. And so these are the core entities that your interface or your API are going to exchange, and that your system is going to persist in the data model. So in our case, some of the core entities are, of course, the text data, that's our output, as well as URL metadata, the URL itself, and metadata about whether we've crawled it or not. And then we'll probably also want some domain metadata. And this is so that we can adhere to those policies in robots.txt, which are at a domain level, not a URL level. So you may know these right away. For user-facing product type system design questions, these are more straightforward and reasonable than in infra questions, but they're still useful to outline nonetheless. And so next up, we go over to that API or interface. Given that this isn't a clear user-facing product that has user-facing APIs, we're going to choose that interface route. So we'll write interface here. And what this does is it just outlines the basic inputs and outputs of the system. So you want to clearly outline what data the system receives and what it outputs. And this establishes a really clear boundary of your system's functionality. So we can say in our case, the input is going to be a set of seed URLs, maybe that URL metadata. And then the output is, of course, going to be that text data that we parsed from all of the websites. So hopefully relatively straightforward up until this point. And now the more interesting bit is this data flow, which is dotted here again because it's optional, but makes a lot of sense for this style web crawler infra type question. So we're going to come down here and we're going to add a data flow. And what the data flow is it describes the high-level sequence of actions or processes that your system performs on the desired input in order to produce that desired output. So this is really just a simple list, and you're going to use this flow then to inform your high-level design moving forward. So let's look at what ours would look like. In order to construct a web crawler, the very first thing that we do is we take those seed URLs from a frontier set, and we request the IP from DNS. And now, frontier, I should define this. Frontier is the set of URLs that are yet to be crawled. So in the beginning, this is just our seed URLs. You have some set of seed URLs. We're going to pull each of those URLs off the list, and then we're going to go fetch their IP from DNS so we can hit those websites, of course. And then the second thing is that we're going to fetch the HTML. We're going to go fetch that page. Straightforward enough. Next up, we're going to extract text from that HTML. Okay. And then fourth, we'll store that text in a database. Fifth, we're going to need to extract the URLs in the text, right? So whatever URLs were in that web page, let's extract them and add to our frontier. And then lastly, this is the recursive bit. We're going to repeat steps 1 through 5 until all URLs have been crawled, until the frontier set is empty. So of course, I wrote these really quickly because this was something I've done so many times. It wouldn't be so quick for a candidate, and it oftentimes isn't, and that's fine. Core entities would have been pretty quick, interface pretty quick as well, and then data flow is where you spend some time, maybe 5-ish minutes, really thinking through what are the steps here. What do I do when I start with a given seed URL? How do I get to my end goal of having all of this text in a database? And this is the loose process that you might arrive at. Now you'll notice that this is a really high-level process. That's intentional. It's the high-level process that's going to inform now our high-level design. There's going to be far more steps to this once we get into more detail into those non-functional requirements. But this is our starting point. This is how we unblock ourselves. This is how we sit here and just think really critically, what are the simple steps to make this happen so that I can now head to the whiteboard and start diagramming them out. All right, so we've spent the first 10 to 15 minutes of the interview kind of working on the setup here, defining our requirements, understanding our interface and our data flow, all for us to be able to now move into that high-level design. And so if you're a mid-level candidate, then maybe you spent more time here, 15 or so minutes. If you're a senior staff candidate, this part probably went pretty quick, and maybe you're getting to this high-level design just 10 minutes in or so, leaving yourself plenty of time to get into the interesting stuff. In either case, we're now moving on to this high-level design where we're going to focus on getting a simple system up and running that satisfies those core functional requirements. And to do this, we're simply going to follow that data flow that we outlined. And then we're going to improve on this later as we go. So let's have that data flow close by to the left of us here. And let's think of a simple system that can meet this. So the first thing that I'm going to do is I'm going to add some sort of a queue. And I'm going to call this my frontier queue. And so this could be Kafka, it could be SQS. We'll talk about a little bit later on which is going to make most sense. But for now, I have some message queue. And this is going to start by having my seed URLs. So it starts with the seed URLs in this queue. Okay, great. Now, we're going to have some set of workers that pull off of this queue. So we'll have a worker here. This guy I'm going to call our crawler. And what it's going to do is it's going to pull a URL off the queue, and then it's going to fetch the web page, and then it's going to extract the text, and then it's going to extract the URLs. So that's all the things that this really simple, big computational resource, our worker here, is going to do. And in order to do that, it's going to reach up here. It's going to need to hit some DNS, and then go up here and actually fetch the web page itself. So the actual web page. And then once it gets that text data, then this worker, this server, is going to write to a database here. And in this case, we're going to want to use blob storage, of course. So I'm going to go with S3. And this is where we're going to have that text data. So we're going to store that in there. And then any URLs that we pulled off of that web page, we're going to put right back into our frontier queue. So this is going to be put extracted URLs back on the queue. And then just repeat, repeat, repeat. And so I'm going to kind of mark this as these are the things that are within our system. DNS and the web page are external to our system. But ultimately, this is a really high-level design of a web crawler. And so you might be watching this thinking, wow, this is so simple. This YouTube video might not even be relevant to me, how simple this is. Hang tight. We're going to now go into our deep dives, which is where we're going to spend the majority of the remainder of the interview, making sure that this very simple system, which currently meets our functional requirements, is able to scale to meet our non-functional requirements, handling fault tolerance, politeness, efficiency, scalability, etc. So this is where things are going to get fun. As we move on to the final step, the deep dives here, and for this interview, it's the place where we spend the majority of the time, it's worth outlining the expectations in the interview for different levels of candidates. So it's the case that for mid-level candidates, your interview should really have a lot of breadth, 80% breadth, and maybe 20% depth. And so that means that you've gotten to this high-level design, you've hopefully been able to talk through it. It probably took you maybe a little bit longer to get here. And now you're in a conversation with your interviewer. They're going to maybe be leading you in the direction of some of these pitfalls. You'll also be referencing your non-functional requirements and hopefully still leading the conversation where it makes sense. But there's a bit more of a back and forth, and it's totally okay if you don't see all of the bottlenecks or issues and they're pointing things out. You just need to be able to answer those questions competently and evolve your design accordingly. On the other end of the spectrum is staff candidates, where they should get to this point much sooner and kind of confidently go one by one through those non-functional requirements, knocking each of them out independently, while of course still leaving room for the interviewer to provide any feedback or point them in any directions where necessary. This shouldn't be a monopolization of the conversation ever. And then senior candidates, they fall somewhere in the middle there. So it's important to note the degree to which you are proactive in this section is a consequence of your level. And I'll kind of talk throughout about what I'd expect from each level respectively. But what we're going to do is that we have these deep dives that want to satisfy our non-functional requirements regardless of your level. So you're going to come here to your non-functional requirements and you're going to look first at fault tolerance. So this is how can we ensure the fault tolerance such that our system's robust and we don't lose any progress. So zooming back into our design, and I'm going to get rid of this dotted line. The first thing that you're going to notice is that this crawler is doing a lot. It's pulling URLs off the queue, it's fetching the web page, extracting the text, extracting the URLs, etc. And the difficulty here is that if any of these given tasks fail, then we've lost all the other progress. And so this isn't strictly true, of course. We could fetch the website, store it in S3, and then if this thing failed, we would still have that URL in the queue. We'd pull it off in the crawler would check, have some condition. Have I already fetched this? If yes, go get it from here. Otherwise, get it from up here. And that's possible, but there's a number of limitations to this. The first is that we have no separation of responsibility. So this doesn't allow us to scale each of our workers independently. It also really inhibits overall observability and monitoring because we can't have a clear understanding of where we are in each stage. And it also makes us subject to fragility as it pertains to changing requirements. So for this reason, if you get a data pipelining question like this, your first thought should be, how can I split this into smaller, more reasonable stages? And in our case, the most reasonable thing to do is to split this into at least 2 phases, where that first phase is to fetch the HTML, and then the second phase is to parse that HTML, of course storing the text, and put in the extracted URLs. And the reason for this natural breakdown is because the most difficult or the most error-prone process here is the fetching of the HTML. So we want to really isolate that as a single task. Fetch the HTML, understanding that web pages will be down, they'll be throwing errors, they'll have servers that are slow to respond, we'll get rate limited, etc. So let's have this crawler really focus on that singular task, store that raw HTML in S3, and then we're safe. We've done that first hard thing. And then we can put it into the second stage of the pipeline and retry as many times as we may need to the parsing, the extraction of the URLs, etc. on the HTML that we've stored, as opposed to having to go crawl it again. So let's make that update here briefly. So I'm going to have S3 for HTML data. And so the crawler here is simply going to pull off the queue and fetch the web page. And then it's going to save that HTML into the HTML data. And then it's going to need some additional, state here. And this is going to be that URL metadata. We kind of alluded to this earlier. And so you can imagine a URL table. Maybe it has an ID. Maybe the primary key is just the URL. It's not too important there. And then relevantly, it's going to have that link to S3. So that S3 link to HTML, right? That's going to be important. And so the first thing that this guy does is that it crawls, stores that raw HTML data in S3, and then updates the URL metadata. And this really could be anything. This could be DynamoDB. This could be Postgres. It doesn't matter. This is quite simple. There's kind of no strong requirements there on the database type. And then, like I said, update the URL status. So once we've done that, then we want to introduce our second phase. So I'm going to put our second phase down here. This is going to be a new queue. This is going to be called our parsing queue. And so we'll kind of delineate each stage here with a new queue. So put that in there. And so what we're going to put in the queue is going to be that link to S3 or the URL so we can fetch the HTML data. Importantly, you may be wondering, why don't I just put the HTML in the queue so that my parsing worker can then pull that HTML directly off the queue and do its job? And the reason for this is that Kafka actually by default supports messages of size 1 megabyte. Now that could be configured. You'll remember that we said our average websites were 2 megabytes. But in general, it's best practice to minimize the size of the payload that you put on the queue here for efficiencies. So these queues are not meant to have large bytes of data. That's what blob storage is highly optimized for, of course, right? So instead, the pattern here is that we typically just put a pointer to that blob storage in the queue. And so in our case, maybe what that is just some JSON blob of the URL and the S3 link. And by putting the S3 link directly in here, then we don't have to go fetch it from URL metadata. We just have a single fetch from our parsing worker to go get the HTML. So maybe I should instead fetch the HTML from S3 link. And now this parsing worker, now this parsing worker has that HTML. That's the first thing that it's going to do. It's going to parse. So it's going to extract the text, right? So this takes raw HTML, breaks down that DOM, breaks down that tree into just the text that's relevant, and then save that text, and then extract URLs from that text. And so we can then take those URLs and put them back into our queue, which means that this guy is no longer needed. He got replaced by this big loop. Fix up my drawing a little bit here. And so just to recap, we have our frontier set, which has some URLs in here, starting with our seed URLs. Our crawler pulls off that URL, fetches the website. This is the raw HTML, saves that raw HTML in S3, and then updates our URL metadata into a URL table where we importantly have that URL and the link to the HTML. We then also put on the next phase's queue, the parsing queue, that URL and S3 link, or maybe just even the S3 link. And then our parsing worker will pull off of this queue for the next phase, the second stage and last stage in our pipeline. It's going to fetch that HTML and then do the extraction, put the URLs back on the queue. And then importantly, the second thing that it's going to do along this arrow is, of course, store the raw text. So this is going to be S3 that's going to have both the raw HTML first and then the final text data. Now, conveniently in this pipelined approach, we're also now robust to any changing requirements. So you can imagine maybe that the ML team comes back and says, all of this text is great, but we actually also want the text from OCR, the text from images, or maybe the alt text on images in the HTML. And our parsing worker on the first go around didn't consider this. So instead of having to recrawl the entire internet, now we just need to load up all of our URLs into our parsing queue, update our parsing logic, and rerun that. So that's far more robust. That's far better than having to go do that kind of expensive, sloppy fetching of the web pages all over again. Great. So continuing on fault tolerance and robustness, what happens if we fail to fetch a URL? Again, internet's a messy place. It's very likely that websites are going to go down. So what do we do in that case? Well, the first thing that we could do, the obvious and bad answer, is that we could just wait a couple seconds in our crawler. So we fetch a website, we get a 500, whatever it is, we get some errors, and then we just set an in-memory timer here to wait 5 to 10 seconds, and then we try it again. And so this sucks for a couple reasons. If our crawler goes down, then we lost that timer. Of course, it was just an in-memory timer. And then it's also true that that web page may not be ready in just 5 more seconds. In fact, it probably isn't. If the site's down or if the server is having issues or it's overwhelmed, then it could be ready again in 5 seconds, but it also may not be and very likely may not be. So instead, we need a more sophisticated retry strategy, something like maybe an exponential backoff. And so to accomplish exponential backoff, we're going to need to introduce some sort of state. And we can manage this backoff in Kafka itself if we assumed that our frontier queue is Kafka, which is one option. We still haven't made a decision there. And so interestingly, Kafka does not support retries out of the box. We would need to implement them ourselves. So you could have a separate topic here in your frontier queue, and that separate topic would be for those failed URLs. And in order to know how much to back off for each of them, we would determine that backoff time in our crawler and add that to the message that we put back on the queue. So then when the next worker or the next crawler pulls off of that topic, it's also going to have the amount of time, not the time that it should wait, but the time that it should run, more importantly. And it's going to wait until that time to then go try to fetch or refetch that URL. If it fails again, then the crawler has some logic to increase that time in an exponential way and put it back onto that failed topic. So this way, if the crawler goes down, the message will still be processed just by another worker who knows that right time because it's in the message. So this works. It's just a bit of a mess. And so what we could do instead, which is wonderful, is that we can use Amazon SQS here. And in fact, that's what I'm going to do in this design. I'm going to use SQS. And conveniently, SQS actually supports retries with configurable exponential backoff directly out of the box. So initially messages that fail to process are retried once per visibility timeout, and that default is 30 seconds. Now in SQS, a visibility timeout, I threw a new word at you there, it's just the period of time when other consumers are prevented from receiving and processing messages. So if a crawler pulled something off, then the visibility timeout prevents anyone else from seeing it. I'm actually going to go into that, I think, a bit deeper here really soon. But this timeout, this visibility timeout, increases then exponentially after each retry attempt. So we put it back on, 30 seconds, and then 2 minutes, 5 minutes, becomes 15 minutes. And this solves us needing to implement that ourselves in Kafka by just configuring it via a configuration file with SQS. That's awesome. So this is great, but we're not totally out of the woods just yet. The thing that we need to consider now is that we don't want to retry indefinitely. That would be foolish. The reality is that maybe after our 5th attempt, this site is just offline. It's an old URL, it's a bad URL, that server no longer exists, this website's gone out of business, whatever it may be. So you want to set some maximum. And maybe we want that to be 5 attempts. And this can be set again just via an SQS configuration file. It's the field approximate receive count is what it's called. But you could set that to 5. And then what that does is that if that 5 is reached, if that approximate receive count is reached, then failed URLs are automatically moved to a configured dead letter queue. And so you'd have some dead letter queue. In our case, in our AWS ecosystem, we'd have some dead letter queue here. This is just another message queue. These dead letter queues are they're special types of message queues, I guess you can think of them as, that store messages that can't be processed. So on 5th attempt, let me just put it here. Why won't it let me type? So on 5th attempt, move to dead letter queue. I'm going to put that right there. And so we'll retry with exponential backoff via SQS. On 5th attempt, we'll go into the dead letter queue. These dead letter queues are probably web pages that are down, so we don't care about them at all. We could talk to the product team or whomever else to say, what do you want us to do with these? Is there something special? But that handles that. So there's really no expectation from any level of candidate that you know that level of depth or intricacies about the difference between different message queues, Kafka and SQS. That is one potential area where you can show a lot of technical depth. And so if you're a staff candidate, I'm expecting to see technical depth in 3-ish places, and maybe you have a lot of experience with message queues, so you could have shown that depth there like I just did. Fantastic. That's one of your places. Senior candidates, I want to see like 1 to 2 really deep places. Again, that could have been one of them. For mid-level candidates, the expectation for that level of depth is a lot lower. So alternatively, if you didn't know this level of detail, then what you would have derived is just that an in-memory timer certainly won't work. I'll need some exponential backoff. And maybe that solution that I mentioned about just keeping it in a separate topic with state about when to run it is totally sufficient. And that would have been a great answer, both at senior and staff, and of course at mid-level. And then you'll just need to look for other opportunities throughout the interview to go into more depth. Now we keep talking about what happens if a crawler goes down. We should probably go into a bit more detail there. So what happens if one of these crawler workers trying to fetch a URL and one of them goes down? Well, pretty simple. We're going to just spin up a new crawler. That part's straightforward. The good news here is that the URL is going to stay in the queue until it's confirmed to have been fetched by a crawler in the HTML stored in blob storage. So even though a crawler we say it pulls off the queue, pulls a URL off the queue, strictly speaking, this is a little bit inaccurate. That URL will stay in the queue until it's confirmed to have been processed, and then it'll be removed from the queue. And so just quickly, the way that actually happens, because I think this is pretty interesting, is different based on message queue. So in the case of Kafka, what happens is that each message is uniquely identified by an offset, and then crawlers are all part of the same consumer group. And consumer groups are used just to ensure that a given message is read only once by any given worker in a consumer group, which is what we want here, right? So we don't process the same URL multiple times. And then when a URL is successfully fetched, meaning we've stored it into S3, then the worker needs to commit that offset back to Kafka so that other crawlers know that message has been processed. And then that message is committed, others won't pull off it. And then messages are only deleted based on some configurable retention policy. So I think the default retention policy in Kafka is 7 days. This can be changed. And so that means that those messages that have already been read are going to be deleted after 7 days. I think in Kafka, you can also do this by size. I want to say like 10 gigabytes is the default. Nobody quote me on that. I might be making it up. But I think that if this queue gets to a certain size, then we'll also start to delete some of those messages that have already been confirmed to be read. So that's the way that Kafka does it. Of course, we decided in our case to go with SQS. SQS uses that visibility timeout that we talked about. So messages basically remain in the queue until they're explicitly deleted, and instead we use that visibility timeout to just hide messages. So you have that default visibility timeout. One crawler pulls it off. Say that timeout's 30 seconds. That message is still in the queue, but it's quote unquote invisible to other crawlers for 30 seconds. If this crawler went down, the one that pulled it off, then after 30 seconds, that visibility timeout's elapsed. It can be seen now to be pulled off by other crawlers. That's the way that it works there. And then if the crawler is successful in storing the HTML, then it can issue a command back to SQS to basically delete that message off of the queue. That's the way that it works there. So again, you don't need to know this level of detail necessarily in your interview. It's one place where you could go into depth. You certainly shouldn't waste an exorbitant amount of time on it. But I think it's really interesting and good to know. So do want to share it with you all. So with fault tolerance and robustness checked off our list, boom, we can move on to the next one, which is how can we ensure politeness and adherence to that robots.txt. So first off, let me come over here and show you all an example. I'm going to zoom in so you can read an example robots.txt. So again, robots.txt is a file that can be on each of the web servers that specify rules per domain. So here's an example. The user agent line specifies the crawler that these rules apply to. So in this case, star just means this applies to every crawler, whether you're Google or whomever else. And then disallow says the paths that you're not allowed to crawl. So you can't crawl any path in private in this case. And then the crawl delay specifies how many seconds a crawler should wait between requests. And this is in seconds. So between crawling any 2 pages on this domain, we need to wait 10 seconds. It's a long time, but this is what a robots.txt looks like. So what we're going to want to do then is that anytime that we fetch a domain for the first time, we're going to need to go up and get its robots.txt and then add some additional state here. So let me move all this over so that we have some more room. And I'm going to add an additional table. Is it going to let me? Maybe I'll just do it right under this one. So I'm going to add a domain table to our metadata DB here. And this domain table is of course going to have the actual domain. It's going to have the last crawled time, maybe the last time we crawled this domain. And then it's going to have all that information from the robots. So maybe the user agent, the disallow, and that crawl delay. So we'll pull all that in here. So the first time that we fetch any domain, we're going to get its robots.txt. We're going to open up the, go into the URL metadata. This is easy, right? We'll just check if it exists. If it doesn't, we'll fetch it for any given domain, put it here. And then on any subsequent crawls, we're going to look here for any of these rules. And so the very first thing that we're going to do for any given URL is that we're going to check its domain and we're going to see, is this path allowed? If it's not allowed, let me move this over so you all can see a little better. If it's not allowed, then we'll acknowledge the message, essentially moving it off of the queue, removing it from the queue. And so, of course, in Kafka case, this would be, moving the cursor. In SQS case, this would be explicitly deleting that message. It's not allowed. It's something that we can't crawl. The next thing that we'll do is we'll check that last crawled time, and we'll see if the crawl delay exceeds, basically, now minus last crawl delay is greater than now minus last crawled time is greater than crawl delay. Right? Hopefully that makes sense. And if so, we're allowed to crawl it. And if not, then we'll need to put it back on the queue. And in the case of SQS, we'll set that visibility timeout to be whatever that crawl delay is. So we'll wait that amount of time before we do it again. So that's very simply how we're going to adhere to robots.txt. Now, a couple things that are worth calling out. The robots.txt might change. So is it worth us periodically fetching it? Maybe. I'm not going to go into detail there. That's something you could talk about in your interview. Maybe this has some TTL. If the TTL is expired, we go and fetch the robots.txt again. Of course, this read maybe is slow. And so maybe you want to have a cache here that caches that domain-specific data to make this a little bit quicker in memory. Certainly an option. I don't know that it's the most important thing here, considering we're really I/O bound by this web page fetch, but it's something certainly to consider. The next thing that you're going to want to consider is just the general rate limiting to be polite. So the standard limit across the internet is that you shouldn't send more than one request a second. This is sort of the industry standard. So even if no crawl delay is set, as most companies and most websites won't have a crawl delay set, you want to make sure that for any given domain, you're not fetching it more than once per second. And so to do this, we can simply have a rate limiter. We can add a rate limiter here. This can be something like Redis. So it's going to be an in-memory domain-specific rate limiter. So it's going to be a limit per domain. And we can have some like sliding window algorithm, for example, that counts the amount of requests that we've made in the last second and make sure that we don't make more than that number of requests. So our crawler is going to need to also hit our rate limiter here. This should be quick. We're talking tens of milliseconds probably. Check our rate limiter, see if we're allowed to crawl. If it's not, then again, put it back in the queue with some visibility timeout. And you'll want to be wise here to apply some jitter. And so jitter is just the concept of adding some random time such that if we had 10 crawlers that all, for example, had the same domain and they all exceeded the rate limiter, they'd all get put on the queue. They'd all get pulled off then again around the same time, potentially. They'd hit the rate limiter again, only one of them would get through and that process would repeat. And so by introducing some jitter, we introduce randomness and make sure that that doesn't happen. So here's a simple setup that is totally reasonable. Now, you might notice that even with jitter, you run into this problem where when you extract URLs from a given website, there's a very high probability that many of those URLs are from the same domain. So you put them on the queue, and then you have in your queue this backlog of maybe 20, 100, 200, 500, depending on the size of the site, URLs all from the same domain. And so they all get pulled off by the same crawler. They all hit either a crawl delay or a rate limiter, and they all get put back on. And this is inefficient. It's wasted cycles. And so that's true. One area for potential depth here that I've seen candidates go into is that they recognize this problem. And their suggestion basically, and I'm not going to put this in my design because I don't want to go into too much detail. It's a bit abstract, even when candidates propose it. But you basically have some scheduler here. Call it a smart scheduler. And what it does is that instead of putting these URLs directly back on the queue, we'll put these URLs just directly into the metadata. So there's more URLs here, and maybe we have some additional state that says crawled or not crawled, maybe a last crawled time on any given URL. And so the smart scheduler then, what it does is it needs to go fetch URLs periodically, maybe every time this queue gets low. It's going to fetch URLs from the URL metadata, and then it's going to make some smart decision based on an algorithm that you've crafted as to the order of those URLs that you're going to put back on the queue, or make this a priority queue and similarly assign some priority. Kind of same thing there. So this smart scheduler is responsible for making sure that we avoid that case where all crawlers are going through the same domain over and over again, hitting the rate limiter and hitting the crawl delay. So this is definitely a smart thing to do. Just for simplicity, I'm going to exclude it from my design, but it's absolutely valid, a good conversation, and something that particularly staff candidates, even senior candidates, maybe you want to bring up in the interview if you want to go deep on this particular problem. All right, so that should cover politeness. So now we can move on to scale to 10 billion pages and efficiently crawl in under 5 days. And so since scalability and efficiency really go hand in hand, we need to be able to scale in order to be efficient. We're going to tackle those together. It's worth noting that I really recommend you save scalability for the last thing that you talk about. And this is because the system continues to evolve. So you'll note that if we had talked about scalability right away, we would have talked about scaling our crawler, whatever, but we could have completely missed bottlenecks in our parser or our parsing queue, because these are things that we added later. So get your full design down and then scale it at the end. So the first question that we might ask here is that we have a really strict requirement that we need to finish this crawling in under 5 days. So how many machines here, how many crawlers are we going to need in order to satisfy that requirement? And so we talked about in the beginning how you shouldn't do math necessarily up front just for the sake of doing math, but you should do math during your design to inform some decision. And right now I have a clear decision I need to make. I have a clear problem. How many crawlers do I need to scrape or to crawl 10 billion pages in under 5 days? And this would be a time now where we could do math. So I'm going to come up here and I'm going to say up front, this is going to be pretty hand wavy. In reality, what you would do for a system like this is that you would run a test. You would run a test to understand your throughput. And then with the results of that test, you would multiply that out and determine the number of machines. We can't do that in an interview, so I might say that to my interviewer. I might say, in reality, this would be difficult to estimate, and I would actually run a test. But let me do some really crude estimations here. So the top AWS instances, network optimized instances, can handle 400 gigabits per second. And so then we also talked about that each of our pages were 2 megabytes per page. That was our average. So that's what we have out of the gate. So if we had 400 gigabits per second divided by 8 bits per byte, and then we had our 2 megabytes per page, then that's 25,000 pages per second. And so that's a lot. 25,000 pages per second is insane. It's unrealistically insane, actually. You'd be able to do that on a single crawler in under 5 days. Now, the reality is you can never max use 100% of the available bandwidth. That's unrealistic. It's not just unrealistic, it's impossible. And so for our specific use case, this doesn't make sense because we have a lot of other things that are going to happen. DNS rate limiting, delayed response times from web pages. We have the rate limiter ourselves. We have the crawl delay. We have retries. We have all of these things, which make it impossible for us to maximize the total bandwidth. So here's where we get really hand wavy, and we're going to make just some estimate. And I'm going to say to my interviewer, because of all of those things, I think that I'm only going to be able to use maybe 50% of available bandwidth, or maybe even 30% of available bandwidth. And so if we have 30% of available bandwidth, then we have 25,000 pages per second times 0.3, and this is around 10K. Maybe we make that 25%. It's around 10K. Hand wavy math. And so now we have our 10 billion pages, that's 10 to the 10th, divided by 10 to the 4th, where 10 to the 4th is that 10K, and that gives us 10 to the 6th, or a million, total seconds. That's how long it would take us to scrape on one machine, assuming that we can only use 30% of the bandwidth. And so then if we have that million seconds divided by how many seconds are in a day, about 10 to the 5th, this would take us 10 days. Okay? It takes us about 10 days on a single machine. So in order to do this on just 2 machines, it would be, since this scales linearly, we could introduce 2 machines, and this would be 5 days total. We want to give ourselves a little leeway for things to go wrong and for any errors that might happen in our parsing worker. So maybe we end up, instead of 2 machines, we do that times 2, and that equals 4 machines. So we have 4 of these Super Duty network optimized AWS instances that we're going to need here to achieve crawling. And so we can update that here. Crawler will have 4 machines, emphasizing again that that's hand wavy. What about our parsing worker? Well, our bottleneck is actually here on scraping. And so everything downstream of it just needs to be able to scale dynamically. So what we can say here is that this scales dynamically based on the queue. So we don't want our queue to get too large. If our queue has some backlog, then we can pull up more workers here. These can be EC2 instances. These can be Lambdas, kind of any containerized, configurable compute resource here that we can just scale dynamically based on the size of the queue. So you might need to implement some logic in order to be able to do that, but that's the general concept here. This is downstream of our bottleneck, so it just needs to be able to keep up. Now, another potential bottleneck that's often overlooked in this system is DNS itself. So if we're using a third-party DNS provider, we'll want to make sure that we can handle this heavy load. Most third-party providers, they have rate limits, and these rate limits can typically be increased by just throwing money at it. And so given our constraint was that we're super rich, then yeah, that's what we could do. That's totally a valid option. However, it's worth considering what other optimizations here might be. So the first thing that we can do is introduce some DNS caching. So we already had this Redis instance here. So this was our Redis. Wow, why'd the text get so big? We already had Redis here, which handled our rate limiting. And we can just have that same cluster also do some DNS caching. So for any given domain, we only need to hit the DNS server once, and then we can cache those results and just use that cache moving forward. So this is great. This is going to significantly cut down on the amount of requests that we need to make to any third-party DNS provider. And then another thing that we could do, which is interesting, is that we can actually just use multiple DNS providers and round robin between them. So this could help us distribute the load across multiple providers, and would also not only reduce the risk of hitting the rate limit, but reduce the risk of any of those DNS providers having issue. So we could have multiple DNS providers here. And so this approach actually was suggested by a staff candidate that I was interviewing just the other week. And I really liked this idea when they suggested it. It's super simple, but I love how practical it is. So it breaks out of that like traditional academic answer and shows that the candidate's actually thinking practically about real world constraints and real world solutions. The reality is if that staff candidate was sitting in a room with other engineers trying to resolve this problem after they ran into DNS issues, that's probably the first thing they would suggest. Let's just get other providers in there and let's round robin between them. So it's those sort of real practical solutions that oftentimes separate more junior candidates from more senior candidates, because it shows you're not just regurgitating something you read in a book, but instead you're applying a practical approach that either you've done in the past or it just generally shows your practical thinking. Now, focusing back on efficiency, in order for us to be as efficient as possible, we want to ensure that we don't waste our time crawling pages that have already been crawled. And so this means two things. The simple case is that we don't want to crawl the same URL twice. That one's pretty obvious. And then the second one, which is a little less obvious, is that we don't want to parse a web page that has duplicate content of a page that we've already parsed. So this is the case where you have two different URLs, maybe even on different domains, that have the exact same content. And you might be surprised this actually happens way more than you would expect on the internet. It's maybe a depressing fact of the lack of diversity of content on the internet. But nonetheless, those are the two things that we want to handle. So number one, don't crawl a URL that's already been crawled. Let me actually, instead of you guys watching me try to stumble over typing that, let me copy and paste that here. So efficiency, we want to not crawl a URL that's already been crawled. That's the one that we're going to start with. So this one's the straightforward one. We're bound to have a lot of duplicates in this parser when we extract URLs. So we're going to take some web page, we're going to pull all the URLs off of it, and the chances are we've probably already put those URLs on our Frontier queue, or we've already processed them, right? And so the simple thing that we can do here is when we get a new URL, we're just going to check, do we already have it? Do we already have the URL? Is the URL already here? And this should be simple. Maybe actually we make the URL our primary key. We don't need some ID there. And so we just check if it exists. Now you'll note that in our current setup, URLs are only added here after they've successfully been parsed. Then we add the URL. So as it stands right now, we may add a bunch of duplicate URLs to our Frontier queue actually. So you could add another check here in the crawler maybe, or what might be best is that we actually just in our parser worker, when we put a new URL in the queue, we also put it here directly into the metadata DB, and we maybe have like a last crawl time. And so your last crawl time would be undefined. When you get a new URL, you'll put it on here, it'll be undefined. And then when we actually parse it, we'll update this with the real last crawl time and with the S3 link, which also would have been undefined. So that would handle that. Make that the primary key. That's easy. You're going to have, what, 10 billion of these? So that's a lot. We're probably going to want to shard this. It'll be sharded on the primary key. Easy. Still a quick lookup. Log in. No problem. This isn't our bottleneck anyway. So that should work relatively easy. Now that second one of don't parse a web page with duplicate content that's already been parsed. In order to do this, we're going to make sure that our crawler doesn't put something on our parsing queue that we've already parsed from a content perspective. So this is going to need a new step, which is to hash the HTML. And so it's going to hash that HTML and then put that hash here. And so it's going to put that hash there. And then we'll want to check, we'll hash that URL, look in our URL metadata, does that hash already exist? If it does, don't put it on the worker. If it doesn't, do put it on the worker. And now the real question becomes how? How do we do that check? And how do we make that check be efficient enough? And so one thing that we can do, and I think this is probably the best answer, is that you can add just a global secondary index. I think we said we were using DynamoDB here. Anything would work, but just to make this all tie together, I'm going to say we're using DynamoDB. And so I'm going to add a global secondary index on this hash. And so this should make this QuickUp pretty efficient. This is going to be log n now. And it should be more than good enough in us to be able to check for that inclusivity. Especially since, we're bottlenecked mostly on this IO, not on this IO. These are going to be co-located within the same virtual private cloud, right? That's what they're called. So that's going to be quick enough. Now, the other option is that we have kind of an auxiliary in-memory hash set. And so this could be that we have Redis here, and then we use a Redis set. And we have a Redis set with those hashes. And so we just need to check then Redis to see if the hash exists, store them there as opposed to in the secondary index. Now we have some issues where if Redis goes down, maybe you want to be writing to persistence. Of course, there's some things that could show up there. We also have the fact that this could be a lot of data. So another place where we could do math, we have our 10, it doesn't let me type in there, okay? We have our 10 to the 10 pages. Each hash is going to be maybe something like 20 bytes or so. And so this ends up being 200 gigabytes of data, which is a lot, but you can have a single Redis instance that's 256 gigabytes of data. So this could still fit in a single Redis instance. Given that we weren't money constrained, like this is great. This would work. Whether it's the global secondary index or this, they're both totally fine. Trade-offs, of course, to discuss in your interview is that this is additional hardware, additional cost, an additional thing to make sure that we maintain fault tolerance if it goes down. This is slower. It's log n. This one is O of 1. And given that this is in memory, nothing goes to disks. This is tens of milliseconds. So that's a good trade-off to discuss. Now, something I see candidates do all the times in interviews, and usually, unfortunately, they don't justify it, but they say, oh, I'm going to use a Bloom filter. I'm going to use a Bloom filter right here. And so, first of all, what's a Bloom filter? A Bloom filter is a space-efficient, that's the important part, space-efficient, probabilistic data structure that's used to check for set inclusion, just like a hash set. So you can basically say, is this thing in a set, just like we're doing here, but in a space-efficient way. So you basically trade accuracy for space efficiency. So it'll be far less than 200 gigabytes, but now false positive matches are possible and false negative matches are not. So in other words, to say that more clearly, a query could return either possibly in the set or definitely not in the set. And so in our case, we're checking, we're saying, is this thing in the set? And it'll return, well, it possibly is. And that's going to have some error margin. And so this means that we could have those false positives where it tells us that something is in the set even though it's not, basically telling us we've already parsed content even though we haven't. And then we won't put it on our parsing queue and we'll lose that content. And so maybe when we're talking about 10 billion URLs, that's not a big deal. There's not going to be a ton of false positives, so who cares? Maybe. Or maybe it really matters that we get all the text on the internet, of which that's a bad option. This is a trade-off, something to discuss with your interviewer. But all in all, given the size and the lack of constraints here, unless my interviewer told me that I need to have a really small Redis instance, I wouldn't even consider the Bloom filter. I don't consider it actually to be a very good option. I bring it up here only because it's something that so many candidates, when I ask this question, talk about. And frankly, I see it almost as a bad sign when they do, because they don't set up the problem. They don't say that I'm memory constrained here in Redis, and as a result, this is my solution. They basically just say, I need to check for set inclusion of a hash, so I'm immediately just going to use a Bloom filter. They don't consider the global secondary index. They don't consider just keeping it in Redis. And it's clear to me that the reason they're doing this is because my guess is that this Bloom filter is kind of prominent in literature, maybe in Alex Shu's books or some of these other things. That's my guess, grokking, whatever. So people are kind of just used to regurgitating that. And it shows that, sure, they've read some things, but they're not really thinking thoroughly about what the best option here. So I personally would go for the global secondary index, but this is also totally fine. Now, the last thing to round out efficiency is that we just want to be aware of something called crawler traps. So these are pages that are designed to keep crawlers on any given site indefinitely. They can be created by either having a page that links to itself many times. Of course, we've talked about how we just handled that. But it can also just link to different pages in that same domain over and 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 over again, nearly indefinitely, maybe hundreds of thousands of times or something, all with basically no content on that page. So if we're not careful, we could end up just crawling and crawling and crawling and crawling and crawling on a single domain, not getting any useful information. So fortunately, the solution to something like this is pretty straightforward, and we can just implement some max depth for crawlers. So we can say like our max depth is 20 or something like this. And then we can add a depth field here to any given URL in our metadata. And so every time we follow a new link, we can increment this depth field by 1. If the depth exceeds our threshold, then we're stop crawling. So this will all be done by the parse worker. The parse worker, when it adds a new URL, will check the depth of the URL that it's currently parsing, and then add for the new URL that old depth plus 1. If that depth is exceeded, I don't know why that's a hard word for me to say right now. If that depth is exceeded, then we won't put it back on our queue. So that should be relatively straightforward. Okay, so let's take a look. We handled fault tolerance, politeness, scale, and efficiency. And at this point, there is our semi-beautiful design. This thing covers all of your functional requirements. It covers all of your non-functional requirements. And this would certainly pass an interview at senior. This is far more than you would need to do to pass an interview at mid-level. If you were able to have that initial high-level design that we talked about, and then you were able to kind of competently answer some of my follow-up interview questions about retries or about things going down here, or about how to handle the efficiency of not reparsing the same URLs or content. If you were able to do that, then great. You probably passed as a mid-level candidate. If you arrived at something like this, but without kind of the deep depth that we showed here, or the deep depth that we showed here, maybe you didn't talk about DNS, or there could have been things that you left out. That's probably passing at senior. And then for staff, you maybe don't need all of this, but you needed to show depth in some places. So we showed some opportunities. This could have been a place for depth. We just talked about that. The different types of message queues was a place for depth. Talking about DNS, some solutions there, of course, was a place for depth. So lots of opportunities. There's no strict rule on where those places are. You'll want to find them and make sure that they make the most sense to you, and they're the places where you have your expertise. Now, before I close off here, I want to mention what some other deep dives could be. I'm going to paste some of these in here, actually. Maybe I'll just paste this directly off of our website. So, that looks like trash. So instead, I'm going to write them. So some additional deep dives. One is how to handle dynamic content. This is something you might have wanted to ask your interviewer directly up front. So many websites are built nowadays, of course, with JavaScript or frameworks like React, Angular, etc. And this means that the content on the page is not just HTML, but instead it's loaded dynamically with JavaScript. And so to handle something like this, we would actually need to have a headless browser like Puppeteer or something in this crawler, which is able to render that JavaScript before we can extract the page. And so that's going to make this way slower, way more error prone, and way more expensive. But that's something to note there. Another one is how to monitor the health of the system. That's something that you might want to talk about. Of course, splitting it into different phases helped, but you can have monitoring services, Datadog, New Relic, whatever, to monitor where URLs are in each of the phases respectively and what your main errors are. How to handle large files or large web pages. Maybe I'll just say that, large web pages. So some web pages might be huge. Maybe we want them, maybe we don't. They could cause some issues to our system. We can use something like a content length header on the request to just skip downloading large files. That's one option, something you could talk to your interviewer with about. And then how to handle continual updates. This one's more common, particularly if you were told to design a web crawler for like a Google or an indexer, or maybe we're told that we want to retrain this model every couple of months or so. So we want this crawler to continually run. And in this case, I think that best solution is we had talked about that URL scheduler that you might add here, as opposed to just adding things back on the queue. And so I think that's the right solution. You have some smart URL scheduler. Again, it periodically queries your URL metadata database here to determine what we put on the frontier queue, as opposed to putting it directly here. And then we would probably have that last crawled time to just check some logic. If we haven't crawled something in, n minutes, days, hours, whatever, put it back on the queue. So some additional deep dives I'll leave with you guys. Additional deep dives. Of course, those aren't the only ones as well. But those are some good ones. So hopefully you're feeling good. Hopefully this was clear enough and that it made sense. We've satisfied all of our functional requirements, all of our non-functional requirements. We're leaving the interview excited, happy, knowing that we just crushed it, and we're about to land that new job. So kudos. Thanks for following along. Just 5 days. So thank you very much again, everybody, for watching. Really loved the reception to these videos. Going to continue to do it. I know I'm a week late on this one. I was traveling, so apologies. But of course, if you have an interview coming up, particularly at a Big Fang, and you want to get this hands-on practice, I'm biased. I know that. But bias aside, I really think the best thing that you can do is practice with an interviewer who works at some of these big companies and has asked these questions before, and they'll be able to show you exactly what they're looking for. So head over to hellointerview.com, see if it makes sense for you to schedule a mock interview. I'll be looking at the comments as I always do, so please follow up with questions. Anything that you think I did stupid, let me know. Always happy to hear that feedback. And most importantly, best of luck with your upcoming interviews. You guys are going to do great.